Google has recently launched a free MCP server for Google Maps, and they made this beautiful Grounding-Lite demo app to showcase its capabilities. It's powered by Gemini models and is based on the Grounding-Lite MCP server, which is the subject of this tutorial. You can use it to find the best places to visit in some area, or to have detailed information about the weather. Let's ask it, for example, to find some top-rated cafes in Berlin. We get 5 results which we can see are indeed in the right place. We also get a nice summary describing each cafe. We can even ask it about the weather in that area. Here you can see exactly what it's doing under the hood, and in the end we get a detailed report about the weather. You'll find a link in the description for this demo app if you want to try it yourself. Let's now see how to get free access to this MCP server, and how to call it programmatically with our own LLMs. As we said earlier, this is the Grounding-Lite MCP server. It exposes 3 main tools, namely, search places, lookup-weather, and compute routes. It's completely free of charge in this early experimental phase, and it comes with very generous quotas of free usage. You can call the search places tool up to 100 times per minute and up to 1,000 times per day, lookup-weather up to 300 times per minute, and compute routes up to 300 times per minute. To use this MCP server, you just need to activate it on your Google Cloud account. Then you need to create your own free API key. If you don't have a Google Cloud account, you can easily create one and get about $300 of free credits. You can select the default project created for you, or create a new one if you want to. Once you're in the project, you have to make sure billing is activated. You can do it by clicking into this billing section. You'll be asked to link a credit card, but it's only for confirmation and nothing will be charged. Now that you have a project with billing activated, click here to launch a Cloud Shell terminal and click Authorize. This is where we will activate the MCP server by executing these 2 commands. Let's get the first one, paste it here, and replace the value with our project ID, which is this name right here. This will enable the Google Maps API, which is already the case for me. Same with the second command. We paste it, replace the project ID, and this time it enables the MCP server for Google Maps. Let's now close this shell, and proceed with the final step, which is to go to Google Maps platform, and create an API key. You can see I already have my key here. To create a new one, we click on Create Credentials, and click on API Key. And that's it, the API key is created, and we can copy it. If you want to restrict your API key for security reasons, you can click on Edit Key. Here you can change the name if you want, add some application restriction, and more importantly restrict the APIs that can be called with this key. Here we only need the Maps Grounding-Lite API. You can remove all the other ones if you want to. Alright, we have our API key, the MCP server is activated, we can finally move on to the code part. The first step here is to add the API key to our environment file, so we can access it later as an environment variable. As a prep phase, we make sure we have the LangChain MCP adapters package installed, and load our environment variables from the file using this function. Next, we set up the MCP client using the multi-server MCP client class. We put the URL of the MCP server, set transport to streamable HTTP, and use this header to add the API key. This config dictionary is what defines our MCP server. We give it a random name like gmaps MCP, and put it in this multi-server dictionary. This gives us our MCP client object. Now we can use this client to get the tools, which are immediately converted to LangChain structured tool objects, containing the name, description, and full argument schema of the tool. Next, we'll explore each one of these tools in detail and see how they can be used. Let's start with the Search Places tool, and let's look at its input schema. This is what we feed to the LLM, to teach it exactly how to use this tool. We first have a few definitions. There's a circle object, defined by a center and a radius, a lot long object that we use to define the center by its latitude and longitude, and a location bias object which is defined by a circle. These objects are used in the properties which define the payload that is sent to the server. Here there are 4 main arguments: the language, the location bias, the region, and the text query. The only required argument is the text query. Let's now see how we can use this tool by following the schema. One way we can use this is with a specific query in natural language. For example, let's invoke this tool, like any LangChain runnable, with this text query, coffee shops in Paris. We get a list of 5 places as a result. Each place comes with a precise location and a few links to Google Maps for directions, reviews, photos, and so on. The place link will simply redirect us to this place in Google Maps. We also get an AI-generated summary, which describes each one of the results, exactly as we saw earlier in the demo app. A second way that we can use this tool is by giving a general query, along with a location bias, which defines the search area. This is what the payload looks like. In text query, we simply put coffee shops, and we provide a location bias, defined by a center, with its latitude and longitude, and a radius of 5 kilometers. Note that this radius can't be more than 50 kilometers. For the center, let's for example get the city of Amsterdam. We can use this website to get its coordinates. I've already copied them, so they're the ones given here. Similarly, when we send this payload, we get 5 results in the same format. By clicking on the link, we can confirm that the location is indeed in Amsterdam. And again, we get the full AI-generated summary describing each coffee shop. Let's move on to the lookup-weather tool. Again, we look at the input schema. It defines a date object, containing a day, a month, and a year. A lot-long object is defined for the coordinates. And finally, we have a location object, containing either a string address, lot-long coordinates, or a place ID. In the actual arguments of the payload, we have date following the date object schema, an integer for the hour, a location following the location object, and a unit system, which is metric by default, but can also be set to imperial. The only required field is the location. Let's now see how we can use this tool. First, let's invoke it with precise location and time. For location, we put the coordinates of Amsterdam from earlier. For date, let's put the 22nd of January 2026. At the time of recording we're the 21st, so it's tomorrow. We can ask for up to 7 days into the future. For the hour, let's put 16, which is 4 p.m. If we want a specific hour, we can go for up to 48 hours into the future. If we send this payload, we get a very detailed weather report containing the temperature, the feels like temperature, air pressure, probability of precipitation, quantity of snow or rain, speed gust and direction of wind, humidity, and so on. Next, let's try calling it with a general location, a wider time period, and with the imperial unit system. For location, we set the string address to Paris. We keep the same date, but this time we don't specify an hour, and we set metric system to imperial. And here's the result we get. This time we have maximums and minimums for the temperature in Fahrenheit, and daily averages for the other elements, in imperial units. We also get moon and sun events, like the current moon phase, moonrise and moonset times, as well as sunrise and sunset times. Finally, let's look at the compute routes tool. In the input schema, we again define a lot-long object, and a waypoint object containing either a string address, lot-long coordinates, or a place ID. In the arguments, we have destination and origin, both waypoint objects, and we have travel mode, which can be drive or walk. The required arguments are destination and origin. For the usage, we'll again see 2 different examples. Let's first try string addresses in the walk mode. We put Madison Square Garden in origin and Central Park in destination, both in New York City, and we set travel mode to walk. As a result, we get the distance, about 2 kilometers, and the duration of the route, which is a little more than 30 minutes. Let's now try the drive mode, with a mix of coordinates and a string address. In origin, we put the city of Rotterdam in the Netherlands, and in destination, we put the coordinates of Amsterdam from earlier. This time we set travel mode to drive. Again we get the distance, which is about 79 kilometers, and the duration of the route, which is about 1 hour and 6 minutes. And that's it for this tutorial. We've seen how to enable the Grounding-Lite MCP server on Google Cloud, and get a free API key. We then saw how to connect with this MCP server, using a LangChain MCP client, to make it immediately usable with LangChain LLMs as well as LangGraph agents. And finally, we explored the 3 available tools in detail, and saw different ways to use them. For using this MCP server with LangGraph agents, you can check out our 2 previous tutorials where we use the Tavily MCP server, and the Pydantic MCP Run Python server with a LangGraph agent. If you found this useful, don't forget to drop a like or leave a comment with your thoughts, and subscribe to the channel if you haven't already. Thank you for watching, and I'll see you in the next one.